Next up, we have a young machine learner who's also interested in distributed computing, and he got to Clojure by a long road which started in the KDE land and on C++. And he will talk about replicated state. Christian Weilbach.
Okay, I'm very happy to be able to talk today about replication with you. So first of all, a few words about me. My handle on social networks is Weilo. On Twitter, there's this one. So if you you should find me by this. I'm a master's student at University Heidelberg. I'm currently doing my master's thesis about distributed databases and machine learning and something like eventual consistent machine learning. I'm also working as a software consultant with friends of mine, mostly in Clojure, at Lambda Forge. But beyond the technology, I'm also really interested in social relations. So I think this is an important part of the community. And when Rich Hickey spoke about speculation, he mentioned that it's very positive that this community has come together and there's so much effort also to bring newcomers to the field and emphasize it's not a negative community, but it's really understood by Clojure people that this is important, and I really like this. If you are interested in any further information, I can, of course, only give you a quick glimpse of the system and the stuff that I've been working on. You can read it up on the webpage of replikativ, which is the system that I'm talking about. So first of all, an overview of my talk. First of all, we will have a hands-on view from an engineering perspective on state replication and distributed state synchronization. We will talk about some of the requirements. I will give you an example application, show you the code. We will have a quick look at the architecture. I will also say a few words about the implementation. And where Clojure has helped me and where I had some problems, or at least what is difficult when you try to approach a system like this, in my opinion. And finally, I will talk about the bigger picture. So this is then general the role of data, how I think we would like to compose distributed systems, and the general value proposition of a system like this. So first of all, the engineering aspect. I want to start with some frustrations I had, and maybe many people here can share this frustration. I'm not sure. I mean, if you are in Clojure land and you're on the JVM and you manage your state, you're in a happy place. You have software transactional memory combined with persistent data structures, and this gives you really, when I came there from Java and C++, I could drop all the logging. I had read parts of Java concurrency in practice. It horrified me. It's a famous book. It's a really good book, but it's still horrible. So yeah, I mean, people often talk about their system as if it was a single computer, and you had have a strongly consistent notion of how it works. But the problem is that who of you can just work on a single machine with Clojure? I mean, is there somebody? I mean, there are some projects where this might be possible, but very often you have who has ClojureScript clients? I mean, clients talking to some system or just. So this is quite a few people. So once you start to work on this, you have different solutions, but you get distributed, and people tend to think about their system still in a strongly consistent manner. Also, who of you knows the Call Me Maybe series from Afur? It's if you haven't read it, I mean, it's really great. So you have all these eventual consistent databases and systems, and they promise you a lot of stuff. Some things are even impossible, but it's really also difficult to get to the notion of what they provide as consistency guarantees. When I talk about a distributed system, I want to focus on a specific aspect, which as functional programmers we understand really well. But when we come to these other infrastructure distributed architectures like eventual consistent databases, often there are many requirements mixed and many problems that you're trying to solve. But what I'm talking about here are state changes, or what I would, or you could also say these are distributed write operations. So this is the real problem. I would start a rant here. So I would say distributed read operations are basically solved. So if you use the atomic, it's no big problem. You get linear read scaling. All data is immutable. You can just copy it. I mean, I guess many of you have used BitTorrent. It's an amazing piece of technology. And even when I started like 6 years ago to experiment with some of the stuff, it was scaling really well. You could dump whole WikiLeaks pages in there and distribute it and have it totally decoupled from HTTP as long as you were reading. This was some of the stuff that I was experimenting with. This was no problem at all. The problem is if you want to change data. So this is what I'm talking about and what the system is mostly about. So yeah, and one more thing. I said that strongly consistent, for all of you who don't know what this means that you can think of the write operations or the state changes in your system happening in a linear order. So you just have a line and you can draw all the operations on this line. The problem is if you go into a distributed system, this becomes a directed acyclic graph, or a DAG, how it's often called. And this is much more difficult to reason about because you have then concurrency, notion of concurrency. And also if you want to read up on some of the background theory of this notion of time, you can read Lamport's seminal paper from 1978 about time in distributed systems and clock synchronization and so on. So here, but this is not strictly necessary. You have experienced this every day if you work with, this is for instance the commit graph from GitHub from Loom, which is the graph library for Clojure and ClojureScript, and you can see that you have these parallel lines and you have these forks and things happen in parallel and you cannot reorder them afterwards. So there is no happens before relation as Lamport has formalized this for a partial order. So this is what I'm talking about when I say this is a graph. Okay, of write operations. So my motivation is, actually, I think this is very tricky to reason about this. When you have a distributed system, for instance, we started to work on a system with the atomic in the backend. This is nice, you can scale it out and so on. But the problem starts when you have these ClojureScript clients and you have mobile clients and you do remote procedure calls. You have to do the distribution on your own. You have to write a lot of glue code depending on the systems that you work with. This is, for instance, for REST APIs. This is a famous problem. I mean, many famous Clojurians also talked about this. Like Charles Emmerich has a project Guild, for instance, where he has also explored some of this stuff and described in detail how insane it is that people in some situations complain about remote procedure calls and laugh about CORBA and object serialization and so on, and then they at the same time start again building REST APIs, which is same object serialization over wires and so on. So you work on a really low imperative level on the network, and it's really difficult to reason about the system. You have to do your I/O operations ad hoc, so you cannot leverage the Clojure STM, for instance. And in the long run, even if you don't have clients, if you can just use one database solution in the backend, you're really lucky. But often you have to integrate other database solutions. So how do you coordinate then? When I write to this place and then to this place, and maybe something fails, so what are the guarantees of this joint system? How can I compose them and so on? So these problems are still difficult, in my opinion. I mean, there are some solutions that you can apply to a specific space. But yeah, what I really want to talk about now for motivation is prototyping. So the problem is, you could ask, why not solve this problem when you have it? So why thinking even about large-scale distributed systems. Most apps don't even get bigger than maybe a few thousand lines of code, and the project is not successful, and you have, so you want to do prototyping. This is what I also wanted to do initially. Clojure gave me a big productivity boost. I could do live coding, I could build these systems. When I started to work with it, it was really great when going away from Java, but once I had these distributed systems again, I felt all the drag and all the gravity of complexity and imperative state management in the systems again. So I would say that even if you have a small app with distributed clients, prototyping is not exactly trivial to do. I mean, you can do all the remote procedure calls, you can use some library, but often it's still much more involved. You know how to write this kind of code, but what you do usually is you introduce a strong center. So you have some strong central database in the middle, which does all the state coordination for you, executes all the transactions, for instance, Datomic, which is a really cool database. The problem is then you have to build all these central state management solutions, and all the clients have to talk to it. For instance, you cannot do local state changes. So what I really like to do is I develop in Figwheel most of the time, and I will show you this in a minute. So I would like to reason about state locally and avoid this central coordination situation where I have to think how to let part of the systems communicate to each other. So my example application today is a trivial chat application, which hopefully you can see. I will show you first the application. It's not really fancy, but I think you can read this, hopefully. Can you read this? Somebody? Okay. So this is Material UI, very handy if you haven't seen this. If you are not a big UI programmer like me, you can just use some nice UI components. And here, for instance, I would say, okay, I send another hello to Bob. And here these are connected. I will show you in a second. And these automatically converge. And the state changes happen in the browser, and they're just connected through some communication mechanism. So how is this done? This is not relevant. Okay, so this is the server. And this is not, so here you can see, okay, I require some of the libraries that I'm using or that I've built to work with the system. I have some WebSocket endpoint that I connect to, and this is the main routine that I start just with line run, and there's nothing chat specific in here. So I just use a store, I use a memory store for development, which is really easy. I have a server peer, so there are no strict distinctions between client and peers. It just happens that browsers cannot open TCP sockets and so on, so there is some distinction, but on the notion of the system, everything is a peer. And you just start this peer, and then you can connect to it. So if you have a look at the ClojureScript client, I include a little bit more. Maybe I could take some of the stuff out, but what is really important are these parts here again. I include a memory store. This is the API namespace. Maybe this comes from Git, because I started with the Git terminology. So you stage changes and then you transact and so on. Now you directly transact, so maybe I should call it API. But anyhow, I mean, you can include these namespaces, and then again, these are some constants. So the idea is, like for instance in Maven artifacts or in general in Java land, you try to avoid simple conflicts by naming. So here there's a user namespace which is specific for this app developer or this application, and also for this app there is a specific UUID which gives you a unique place in the global namespace. You can just use a random UUID, and then you won't have accidental conflicts later on. Again, here is the endpoint. This is the usual stuff, and then this is maybe the most interesting part, or this is the relevant part. So here this works by streaming. So I use an associative data structure, which is this OR map, where I can store keys and remove keys in an eventual consistent fashion. But I don't really say how you should read this value. I instead store a map, and a Clojure map is actually a function. So we have already seen the talk about homoiconicity. So here we also write something like a very simple eval function or a bytecode interpreter over the changes of our distributed data type. And here we just swap in the atom that we get in this case, and source the new value. So this is, we decide how we want to realize the data that we've written at the time that we want to really access it. For instance, I have a Twitter collector running, which is now running for 2 weeks and has written over 100,000 commits and probably over 1 million tweets right now. And there I just use a synchronization on my laptop here, and I used Atomic with a full text index to do analysis. So I realized the data type in a different way, depending on what I want to do with it. But it's decoupled. I just want to solve the right operation, and what kind of reads I want to do is not decided by the system. It's just doing the right stuff. And here again, I mean, same things. Store, peer, I create the API primitive, I use some adapted core.async. Here I do the streaming. I use this eval map function into this val atom. And here I create a data type, which is similar to subscribing, but you have an instance there that you can write to and it's eventually consistent. I connect to a remote server, which might fail. It doesn't matter. I still can write offline because it's eventually consistent. It solves these problems for me. And this is the only state-changing operation. So here I say, for the specific stage namespace, I source under the user and this ID. Here I use it like a set, so I hash this. This is actually a hash function, a cryptographic hash function, this message, so I just have a set of messages. So it's very, very simple. And the rest is just the usual OM application. I mean, you can find it on GitHub. Here's the React app. It's nothing fancy. It's just the usual code, and I plug this in there, here in the main method, and that's it. So this is what I'm talking about. Okay, and this took my friend 2 or 3 hours maybe to build this. I mean, you have to know, of course, these oh, this was wrong. You have to know, of course, some of the API, but you can focus on writing the UI and just doing this state mutations in a very simple way. Okay, so the architecture. I want to just quickly mention this. When I started, I had no big clue about distributed system theory. So there are different consistency levels. You can read about them. Usually it's linearizable, as I've already said. And there's things like serializable, which is still like a linear order, but it's not necessarily the order that you originally wrote the operations in. It's just reordered. And then there are many formalisms in between, which give you different guarantees. And finally, there is eventual consistency, which is thought as the strongest notion of that you can achieve availability and consistency at the same time, or eventual consistency. So the data types that underlie the system are CRDTs. I recommend if you're interested. First of all, who of you has heard about CRDTs? So great. I can skip this slide. Who of you has used this? Has used CRDTs? Okay. Who of you doesn't care? Well, because you want to build a system. It's interesting at this point when you build this, but usually what you want is an abstraction that you don't have to care about unless you really want to dig into. So I actually don't want to care. I want to use a data management system. It just happened that it really helped me to get a proper theory and a formal understanding. So here what you can see is an X. This is an identity that is tracked over several replicas, 3 of them, X1, X2, X3. In the beginning, they are all 0, so time goes from the left to the right. Sometimes these different replicas, these 3, communicate messages with each other. And in this case, it's the data type is using the max operator as a merge operation. So it is converging in a trivial way. You can also see this on the right-hand side. This is related to lattice theory, which is actually a good thing because you can then just use some mathematics that other people have done. And if you can formulate this in this lattice theory, you can define a data type and can store your data this way. And importantly, you don't have to know all the history to later on resolve this because max is just, it works. So important is that you want to get rid of this duck also on disk if possible. It's often not possible to eliminate all the metadata, but this becomes a performance problem. Okay. So quickly about the implementation. I started work after Euroclojure in Berlin in 2013 because I was really enthusiastic about Clojure, and I had this problem that I thought, okay, I don't want to redo this glue code all over again, and this is really missing in the story, and I want to do this. I had no prior experience in distributed systems development except for some BitTorrent hacks, which were in C++ and so on. It was horrible. It was interesting, but horrible. Yeah, and I thought, okay, I really want to have this in the browser, so it has to be cross-platform. And this was, I wanted to have it, but in hindsight, I mean, yeah, this was a lot of work. I mean, now it's 3 years later. I haven't done this full time, of course, but I've spent a lot of time to build this. It cost me much more time than I anticipated. Also, as I bet on ClojureScript in 2013, which I had to make a cross-platform. Otherwise, different language implementations is really cumbersome. Maybe you could do something similar in Go and so on now, but now I have core async. So the whole system is built on core async, publish-subscribe protocols, network I/O, and so on. I will talk about this in a second. But back then, there was no core async, so I could have failed. If core async wouldn't have shown up, I don't know, maybe some continuation passing style stuff would have worked to some degree, but core async is really performant, it's debugged, it's battle-proven right now, I would say. So yeah, and overall, Clojure is allowed to do me this, to build this system. Still, if you have race conditions in your system, and that's why I have problems with this ad hoc style of, oh, let's just solve this particular bug now in some way, is debugging race conditions. I mean, you can be really horrified that you think, okay, I've now done everything, I've checked all my places in the code and so on. And this is also a point where, for instance, I couldn't find formalisms beyond these CRDT things that would really help me. I mean, they cannot type check this, for instance. But as it was a cross-platform situation, I had to go into this yuck shaving business. So, I mean, I had to build all the infrastructure, which in Clojure you usually don't have to do. You can just use some JVM infrastructure. But then if you want to have it on Clojure, on JavaScript as well, obviously these libraries are not cross-platform. So I have built some abstractions, and as I've built a system, I try to factor out, find the proper abstractions, and reformulate it so I get a toolbox. There's also a reason why I'm here. If you're interested in something similar, but you don't care about the rest, I think it is worth. I really like this decomposing notion of Rich Hickey, that he says, okay, design is about taking things apart. So the better you understand your system, the more it should look like a toolbox that you can assemble and then use to solve your problems, not like a joint system which just cannot take apart anymore. So these are composable systems, and the replication middleware, replication stuff is just a middleware for this network library. So hash is strong cryptographic hashing, so you can just store values, and nobody can fool you in the system by introducing something. You cannot use random UIDs if you have a fairly open system, and I wanted to have this strong notion of value semantics. I have simple key value protocol, which with core async, which I've called conserve, which is very simple. Now I have also an append log, which is fast and so on. But I'm looking at building something more sophisticated, like the hitchhiker tree on top of it. I don't know who of you has heard about the hitchhiker tree. So this is really cool, persistent, durable data structure of David Greenberg, who has worked on. He has built it directly on Redis. So Conserve has a Redis backend, but he has gone for really backend performance, large-scale stuff. So I have to refactor this. But I think it's a very important building block to get better metadata representations for the CRDTs. Also, I've built this networking middleware, which just is a wire, which is 2 core async channels, which are not necessarily synchronized. A very simple notion. And error handling in core async is okay if you have small problems, but if you have a big system, you have this problem that if nobody, I mean, you can use this go try formalism that also David Nolan and so on has talked about, but this is not good enough to go to the Erlang direction. So I talked a lot to people with an Erlang background, and they have this awesome supervised error handling, and they build these distributed databases with it, and I wanted to have something similar. So this is what I try to do. It's probably not perfect, and there are Chris Hauser has a different way of Common Lisp, error handling, and so on. So if people want to argue with me about it, I'm really happy to do this, but I think it's reasonably well. It helps me to have proper stack traces, don't miss any errors, and so on. Finally, what's important when you're interested in this is safety and performance. So this is constant performance. I think it's fairly thread safe, or it's even concurrency safe for core async, and it has proper back pressure, which are important things in these systems. So I want to quickly also talk about the vision, because this is important to me, and this is not just a technical thing, but we have already seen that for Lisp programmers, data is code, and this is really great. But is this really true when you look at society? I mean, is our code the same, has the same value when we build something as the data that's in our application? And I would say no. Because if you look at most IT businesses, this is now the point, they control, own, and sell data in some way or the other. Maybe it's not a good business model to sell the data directly, but you can exchange and hire new programmers, but if somebody buys your company, they usually buy the business clients, and they buy the value that's stored somewhere, the know-how and the processes and so on. And this is in your data. So that's also why Google, for instance, is open sourcing all their machine learning stuff. You cannot do it because you don't have the data. So you need some open system or some system where you can replicate data and share data, and that's the motivation to do similar things in a more open way and exchange it and make it accessible for people. On the other hand, you have a really big open source stack, so this is on the good side. I think something like open source data would be really nice. So this is the direction that I'm thinking in, because now we have these privatized internet silos, and this is also what these REST APIs stand for as a business model. It's not just that it's done in a bad way, I would say, because because people don't know any better, but it's just a way to do it to get value out of it. But then you have usually an abonnement concept. Even if you use some service API yourself, you just get an abonnement to your own data. So hey, you can use this great backend service for your great application and so on, but now they have your data and they manage it. So okay. So what if we could openly clone application state, like in Git, you clone it? I mean, often it's very difficult to get it out of the system. This way it's possible. I mean, I can use this laptop sometime, connect, the server synchronizing, I can disconnect, I can resynchronize, and so on. This is more like a Git-like deconnected workflow with data. You can share the application with state with different other applications. I think this is the real value, to cooperate. And you can also move the writer around. So if you have this decoupling, this is again a technical thing, but it's also a point of control. So you can change actually the infrastructure provider, which does the replication for you. And then you could do statistical analysis with users, or at least in a better way maybe than just some big IT companies. Okay, so these are the value propositions, and then this is my end. You can do rapid prototyping. You can do this right now, and I think this is really helpful. You can do cooperative data management, which I think in the future will be very important. If we don't find something like this, we will have more data monopolies, and we have to figure out the distributed right thing. Otherwise, it's really difficult to coordinate and be cooperative. You can do edge computing. I mean, I've run the system on a Raspberry Pi. And this is not a big problem, so you can also push out part of your infrastructure to the edges, or Internet of Things, as it's often called. And finally, what I'm interested in for my master's thesis right now is to think about smart infrastructure, or distributed intelligence, or fuzzy terms, which sound fancy. But in general, you want to also distribute computation. So there's research in this direction. I cannot go into detail. It's not trivial, but yeah. So this is the perspective. Thank you.